I have some problem. Yes, even opening. I am not used. Can you change that? Rotate the first page, please? What did you use for open it? And the first page, I think, was rotated. Okay, maybe just delete it. Just wait a minute. Is that good? Yes.
Okay, our next speaker is Oliver.
Yeah, just change the name.
Okay, this long and informative title, I hope you guess.
Okay. So I want to thank the organizer for the invitation and the opportunity to give a talk here. So today, what I want to, in this talk, I will present a mathematical study of the overlap distribution for the 2D discrete Gaussian free field, which is also a log-correlated Gaussian field. So in the first part, I will describe the model and give you some basic properties. In the second part, I will describe result obtained in a paper. It's a part of a paper obtained with Louis-Pierre Arguin. And I will show that this Gaussian free field exhibits one-step replica symmetry breaking regime. And in the last part, third and last part, I will discuss the problem of temperature chaos. So in fact, the absence of temperature chaos is not very surprising, but what is more interesting is that the overlap distribution is different from the random energy model. So the first part, so what is a Gaussian free field on a set A included in Z2? It's a Gaussian vector with zero boundary condition and whose covariance matrix is given by the green function. So what is this guy? It's a two-point function. So V and V prime, what you do is that you consider the expected number visits to the side V prime by the simple random walk started at V and killed at the exit time of the set A. Okay. So in our case, the set we will consider, first we consider to be the square 0 times 0, 1. We will take for A the set Vn, which is really so big? Okay. Which is such a box of side length n. And in the first step, study, so that's Vn. And let's say to avoid the boundary effect, we will consider Vn delta, which is a box included in V containing all the points at a distance larger than delta n, delta times n, to the boundary of box Vn. So that is Vn delta. So using classical estimates on the green function, it's easy to see that I will call Vn delta the bulk. We can see that in the bulk, the variance is given by 1 over pi logarithm of the number of points in the big box, plus a little O of big O of 1. And the variance of this Gaussian field is given by 1 over pi logarithm of n divided by the norm between V and V prime to the power 2 plus big O of 1, as long as V is different from. That's why we say that this field is a low correlated Gaussian field. So with distribution like in the continuous case, it's very easy to define this discrete object. So the first result was obtained by Bolthausen, Deutschel, and Jacomin, who studied the first order of the maximum. So if you consider the maximum and divide it by the logarithm of the number of points in the box, it converges in probability to a constant that I denote by square root of g. A second result was obtained by Davio. So that's the first order of the maximum. So it is here, square root of g times log n squared. And a lambda between 0 and 1. And you look at the number of points where the field is large than lambda times the first order of the maximum. You look at the logarithm of this number of points, normalize it by the logarithm of total number of points. So we call it the log number of I points, lambda I points. And you get this convergence in probability to 1 minus lambda squared. Yes, yes. Exactly. So an important remark is that all these results are exactly the same as for the random energy model, which in this case is a family of squared IID random variable. So in this talk, what I will call the Derrida's random energy model is n squared IID random variables, Gaussian random variables that are centered and have variance. The maximum of the variances for the Gaussian free field is from approximately this. So what we want to study is the free energy. So we consider the partition function with sum of e to the beta, the value of the field outside V, and when you sum over V. And what you consider now, the free energy, is it's the logarithm of this. Okay, can I just skip it? Sorry? Ah, it's recording. Okay. So you take the logarithm of this partition function and normalize it. And what we observe is a function like this. So there exists critical, which is root of 2 over pi. Okay. Thank you. So what we see is this phase transition at some beta critical is equal to square root of 2 times pi. And this convergence holds almost surely and in L1. So what is important is that beta larger than beta critical, what we have to understand is that the mass in this sum is given by the maximums. While when beta is strictly smaller than beta critical, the mass in this sum is given by a lot of points where the fields has a value strictly smaller than the maximum. So what you observe here is like energy entropy competition. So the proof is essentially a Laplace method. It's very simple using the results I presented just before. Bolthausen, Dolce, Giacomin, and Davio results. Okay, so keep it in mind. Here, the weight is given by the maximums, and here by a lot of points that are really smaller, like lambda I points with lambda strictly less than 1. And by Laplace method, you know exactly which lambda you have to choose. Okay, so the first result was obtained with Louis-Pierre Arguin. And so I will describe this phenomenon. So what we consider is the Gibbs measure. So it's a measure proportional to the e to the beta, the fields of the value outside V, normalized such that this guy is a random probability measure. And what we will consider is the overlap, what we call overlap. So it's the covariance divided by the variance in the bulk, at least. And using estimates on the green function, you see that this overlap is approximately equal to this. And look here, if you take V and V prime very close, let's say constant, then that's essentially equal to 1. So when you are very close, the overlap is equal to 1. And if you take V and V prime at a distance of the size of the box, let's say a constant times n, then this is equal to 0, almost. So the result we obtain is the following. So what we do here is that we sample 2 points, V and V prime, independently according to the Gibbs measure, look at the cumulative distribution function, take the expectation, and the limits in n. And what we obtain is this limit. So, okay, an important point is that we take beta larger than beta critical, such that the point we sample with the Gibbs measure are very close to maximums. So what I will call here 1 RSB is the following. Limits when n tends to infinity of the expectation that 2 points sample to the Gibbs measure, so beta larger than beta critical. Overlap between V and V prime belongs to some set. Equal to beta C over beta, some explicit constant, time Dirac at 0, plus 1 minus beta C over beta, time Dirac at 1. So the fact why we call this phenomenon 1 RSB regime is because we have 2 possible values for the overlap at the limit. An important, okay, this was proved by Derrida and Spohn for a hierarchical model called branching Brownian motion, which is very close to the Gaussian free field, and conjecture by Carpentier and Ludsal for non-hierarchical fields. An important point is that, again, it's written here, but I can repeat it here in red, is that, again, it's the same as the random energy model. Okay? Okay, so the idea of the proof, I will give a quick idea because I want to focus on the third part, essentially. So the first step is to avoid boundary effect. So we cannot only consider V and delta because the complement of this box, you have almost the same number of points as in the box. So you cannot neglect the Gibbs measure of this complement. So what you have to choose is the points V, so the boundary is larger than n to the power 1 minus rho, for any rho between 0 and 1. And what you get is that the Gibbs measure of this complement, the complement of this set, is 0 asymptotically in probability. Okay, now the proof is the following. The idea is to introduce a perturbed model and to relate the free energy of this perturbed model to the distribution of the overlap for the initial model. So we choose alpha between 0 and 1 and denote by this thing the box centered at V with side lengths n to the power 1 minus alpha, or 2, something like that. And now we consider a new random variable associated with V, which is the conditional expectation of the field with respect to the filtration generated by the complement of this box. And by the spatial Markov property of the Gaussian free field, this is equal to this conditional expectation with respect to the filtration generated by the box. Okay, it's a Gaussian vector, so these two guys are independent. So I write like this. And now, what I think like a branching random walk or branching Brownian motion. There's like a tree structure. Now I am happy because between this time and this time box, I have independence. And so what we do is that we add weights in front of these two guys, sigma 1 and sigma 2. So I have three parameters, alpha, sigma 1, and sigma 2. I choose them like this, alpha between 0 and 1, sigma 1 equal to 1, sigma 2 equal to 1 plus u. You have to think at u as being very close to 0, but positive or negative. So we call x, b, or r the object we want to study, and we call like this the free energy of the Aperture model psi. So this guy restricted to a and rho. So a and rho is here. So, and the relation between both is the following. So if you are able to compute explicitly the L1 limit of the free energy for the Aperture model, then you know this family of integrals. And by monotonicity property of this guy, you can deduce x beta of r from this family of integral. So this is done by Gaussian integration by part and convexity argument to exchange all the limit derivative here. So if I denote by f beta sigma square the free energy of a new realm, let's say, where this time the variance is given by sigma square over pi times log n square. Then we can write the guy we want to compute like this. So there is two cases, depending if sigma 1 is smaller or larger than sigma 2. And we have an explicit expression. And if you know a little bit about two-level Derrida's gram, it's exactly the same behavior you observe. And in fact, indeed, it is explicit because a simple computation gives you this. So it's totally explicit. So I don't want to give the details of the proof, but it's just a comparison with a two-level gram with parameter sigma and alpha. Okay, there is some Laplace method here, and here comparison with non-homogeneous two-level gram. I should define this, but I have no time for that. And Kahn's convexity inequality. Sorry? Yes, I do. Here. And here. Here it's just this guy and these two guys that are explicit. Okay. So now what I want to study is the phenomenon of temperature chaos. So what is this phenomenon? For some models, spin glass models, for example, what you can observe is that for beta large enough, you have several values that are possible for the overlap. And when you choose beta and beta prime large enough but different, the chaos in temperature means that you see only one deterministic value. Most of the time, it's because the pure states depend on the temperature or the geometry of the system. So before starting with this problem, I want to tell you more about the Gaussian free field. So what you have to keep in mind is that in the second part, the one RSB regime, I only use very basic results. and spin glass tools, let's say. I did not use sophisticated results about the Gaussian free field. I did not care about the second order of the maximum. I did not care about the full external process. And I will talk about that now. Okay. So, Brabson, Ding, Zaitouni, in 2013, found, using a comparison with branching random walk, there was a lot of progress in the 10 last years about branching random walk. So using, let's say, inspired by the progress in branching random walk, these three guys were able to prove that the right centering term for the maximum is this guy. And they obtained a convergence in distribution to an explicit non-trivial limit. It was the first time people observed a difference between the Gaussian free field and the random energy model. Because for the random energy model, the right centering term is this guy that I denote by M and rem. And as you can see, here you have a 3, and here you have a 1. Since the Gaussian free field is correlated, it's quite intuitive that the maximum is smaller. Okay? Now, a second very important result is the full extremal process. So I will try to explain you who is this guy. So you sum over V in the box. Here you ask, here should be a U, not a V. So you ask the field at side V to be a local maximum. What I mean by that is that the field is the maximum in the box of side length 2R. Then here I have the normalized position of this local maximum, V divided by N, such that V over N belongs to V. V over N belongs to V, which is 0, 1 to the 2. Here, I have the centered value of the field at this point V, which is a local maximum. And here, I have what I see from this local maximum around it, the neighborhood of this local maximum. So then there exists a random finite Borel measure Z to the V on underline V, and a probability measure nu on R plus to the power Z2, such that for any sequence Rn that tends to infinity, but which is small compared to N, in this sense, we have the following result. The full extremal process NRN converges in law to eta, which is a Poisson point process, with intensity measure given by this. Z to the V dz in my box V, e to the minus beta C H dH for the centered value, and nu d phi for what we will call the law of the clusters, or the decorations. Okay. So how should we think of this result? Given this measure ZV, the position of local maxima when they are scaled are asymptotically IID with low ZV normalized by the total mass. The center value is given by an independent Poisson point process with intensity given by this. And to each of these local maximal, you attach independent cluster whose law is given by nu. So, what is the next slide? Okay, Biscap-Noether study and characterize this random measure and Z to the V and give an explicit description of the cluster law nu. So if I want to draw a picture, I will compare now the picture for the REM and the Gaussian free field. that's my box V. So if I look at the RAM, what I have, okay, I can see, because that's the value of the fields. Let's say like this. So you see very well separated maximums. When you sample it according to the Gibbs measure, there you pick the same maximum, so the overlap is 1. You pick 2 different maximum, and the overlap is 0. Of the system, because the overlap is 1. So these distances are all of the order of the system, constant time n, let's say. And if you look at the 2D GFF, what you see is clusters around the maximum. So you also have a maximum, but then you have a couple of points around it. I had simulation, but it was too heavy for my beamer. So I decided to draw it. Okay. So that's the difference between the RAM and the 2D discrete Gaussian free field. So here you have clusters around local maximums because of the correlation. Okay. So the first result, which is not too difficult to prove, is the following. If beta, consider beta and beta prime, two inverse temperature. If one of them is smaller than beta critical, then for all A, we have 0 at the limit in L1. So this is easy to prove using what we did with, it was a joint work with Michel Pin, which was a student in Paris and will be a postdoc with Paul Bourgade in New York. So this is easy to prove using the same result that we prove for beta equal to beta prime with Louis-Pierre Arguin in the paper I mentioned before. And this second result tells us that if beta and beta prime are strictly larger than beta critical, then we pick 2 points, we sample 2 points U and V according to the Gibbs measure at temperature for beta, and U for the Gibbs measure with beta prime. You look at the cumulative distribution of this overlap. You tend to some Q beta beta prime in distribution, where Q beta beta prime is given by this. So the psi k are the value of my maximums, the Poisson point process with explicit intensity, and the phi xk are the relative position of, k is some point here, let's say it's this guy k, and phi xk is the relative position of all the guys in this cluster. So what does it mean? When you ask, you pick A strictly positive. So looking at the overlap being larger than A means that you want, remember this picture, means that you ask the 2 points to be in the same cluster. So you choose a cluster and you ask the 2 points to be in the same cluster. Not on the same point in the cluster, but in the same cluster. And here it's because you have the normalization, because we are considering a Gibbs measure. So in fact, what we obtain at the limit is, a limit is delta 0 if one of the parameters is smaller than beta critical, and it's 1 minus Q delta 0 plus Q delta 1 if beta and beta critical are strictly larger than beta and beta prime are strictly larger than beta critical. So we don't we do not observe the phenomenon of Kao temperature. But it's not surprising because here, as you can see, the geometry around the local maximum do not depend on the temperature. There is nothing depending on the temperature. Okay, so that's what I just said. Q beta beta prime is the probability of choosing 2 points in the same cluster. So, and the proof of this is when you have the full extremal process convergence, it's only 3 pages computation. It's not very difficult. Okay. So now what we want to do, remember, all what I explained in the second part was the same as for the random energy model. To see a difference, you have to look at the second order of the maximum or the full extremal process. So the question is, okay, if beta and beta prime are equal, we already know that it's the same as for the REM. What happens if we choose beta and beta prime different? So what is the story for the REM? So for the REM, again, we define an overlap, which is the covariance divided by variance. But since the random variables are independent, which is what is written over there, okay, it's just an indicator function of u to be equal to v. So Irina Kurkova proved in 2003 that if beta and beta prime are larger than beta critical, then you get this convergence. Again, you sample 2 points according to the Gibbs measure, look at the overlap, the cumulative distribution function, and you have this convergence in distribution to this guy, which is explicit here, and where the psi k are again the atoms of a Poisson point process with explicit intensity, which is the same for the Gaussian free field. Okay, so the idea is to compare now these two guys. So keep in mind this expression, which is quite heavy, but I will simplify it. To do this, I introduce x beta of k, which is this guy, such that you can rewrite q beta beta prime like this. So here we have translation of the atoms of the Poisson point process. By independent, these guys are independent of psi k because they depend of the decorations, which are independent of the Poisson point process. But since they depend of the decoration of the k's atom here, these two guys are correlated. Okay? But if we take beta equal to beta prime, then there is a result, at least from Rose-McKenna and Eisenman, that says that if you translate your Poisson point process by independent IID random variables having enough moments, then the atoms are equal in law to the same translated by a constant. So here, if beta is equal to beta prime, you can replace all these x by a constant. And then you simplify, and what you get is that q beta beta prime is equal to this. So it's the same, which coincide with the weaker result obtained with Louis-Pierre Arguin. So now the question is the following. What happens if beta is different from beta prime? The answer is that they don't have the same distribution. And we were able to prove that if beta and beta prime are larger than beta critical but different, then the expectation that for the Gaussian free field that the 2 points are in the same cluster is strictly smaller than the same quantity for the REM. So why? Because a pure state is just given by 1 point. So they only depend on the value of the field at this point. So if a point is likely for beta, it is also likely for beta prime. That's the intuition I tell you. But for the discrete Gaussian free field, you have these clusters. And the pure states depend both on the height here, but also on the geometry of the cluster. What I mean by that is the size of the cluster and the value of the field in this cluster. And again, here there is some energy entropy competition. Because if beta is very close to beta critical, you can imagine that in the cluster, only the large values are important. But if beta is large, it's possible that the cluster is big. There is a lot of points where the value is small. But when you sum all of them, it's larger than few points. So it's possible that these pure states for beta close to beta critical, but unlikely for large beta, and vice versa. So the geometry of the clusters is important here, and that's explain why we have this result. So that's the picture we have in mind. So fix beta prime larger than beta critical, strictly larger. And we look at these two guys as functions of beta. And as you can see, okay, when beta is smaller than beta critical, you have 0. But these two functions of beta coincide only for beta equal beta prime. Then you get 1 minus beta c over beta prime, like for the rem. Otherwise, this guy is strictly smaller than this one. The proof is the following, where I will first present 3 lemmas. So remember this. Okay? But now we have 2 translations. They are different, but they are correlated. So that's the problem. And as you will see in the second lemma, we cannot deal with 2 different translations that are correlated. So the idea is to use this first lemma. We denote by C beta this constant that appeared before the translation. And we denote by Y, a random variable defined like this. E to the f of Y is given by e to the minus beta critical times x beta, f of x beta prime minus x beta, divided by this normalization term. Then, here we have 2 different point processes. And they have the same, this guy has the same distribution as this guy. So again, here this random translation disappear. We only have the constant. Here we have the same constant. And here we have these yk that are IID with the same law as y, defined like this. What is very important is that, again, y is independent of the psi k, which is not intuitive at all. And the idea of the proof is just computation of the Laplace transform of this point process via the exponential formula for Poisson point process. A similar result was obtained by Panchenko and Talleyrand in 2007. Okay. So the second lemma is the following. Consider 2 sequences of 2 non-increasing sequences of non-negative numbers. So you can think at weights that are ordered in a decreasing way. And we ask the first sequence to sum to 1. And then what we do is that we consider an as a random IID sequence of positive random variables. And we write Pn tilde like this. So what we do is that we put weights, an, random weight, in front of Pn. And we normalize it such that the sum of the Pn tilde is again equal to 1. Then we have that the expectation of the sum of Pn tilde times Qn is smaller than the sum of Pn times Qn. And if A1 is not almost surely constant, plus some additional weak assumption, then this inequality here is strict. The idea behind this is that we can write this as an inner product for 2 sequences. if you want to maximize it, you have to order both sequences in a decreasing way. And the fact that you randomly perturb Pn, we denote this random perturbation by Pn tilde, this disturbs the ordering of Pn, so the shared ordering, and then tends to reduce the inner product. So it's not so surprising that you have this inequality. The proof is computation, let's say. Okay, a third lemma. The last step to conclude is to prove that the good A1 that I will choose here is not almost surely constant. To do this, we use the explicit, let's say, explicit description of the law of the cluster given by Biscup and Louis-Dor. So for any fixed y, and then the conditional law of the cluster at site y, given the value of the field at all other point x, is a normal law with mean 1/4 of the sum of all neighbors of the value of the field at all neighbors of y, with variance 1 and condition to be non-negative. So to do this, it's you use essentially the description of the law, the law of the cluster nu obtained by Biscup and Louis-Dor. And then a corollary is that the random variable y is not almost surely constant. And now to finish the proof, what we do is that by the first lemma, we can rewrite the expectation of this guy like this. So we have only one. Okay, sorry. Why? Just let me make a remark. Here, I just perturb Pn. I can ask what happens if I perturb in the same way Qn. Like Qn tilde equal to Bn, Qn, sum over k, bk, qk. So I perturb both sequences. If I do this, and here I look at the expectation of the sum of Pn tilde times Qn tilde, this result is not true. That's why I cannot work directly with this, because here I will perturb both sequences. That's why I use this lemma that allows me to go from a double perturbation to a simple perturbation. So here I rewrite this using the first lemma. I assume that the atoms of the Poisson point process psi k are ordered in a decreasing way. Then it's clear that I will write e to the beta prime psi n divided by the good sum for Pn. I will perturb it by e to the beta prime times yn, here and here, and Qn for this guy. And then what I have is exactly here the expectation of Pn tilde times Qn. And since yn is not almost surely constant, it is the same for an, so I can apply the third lemma and then the second lemma with this choice to prove that when you condition on the Poisson point process psi k, you have this inequality that holds almost surely, because the yn are independent of the psi k. And then, since this inequality, this strict inequality holds almost surely, you just have to take the expectation to prove the results. And thank you very much.